In this video, I'm going to be going over what are called optimization problems. And in these problems, what we're going to be doing is we're going to be trying to find when a scenario gives us the greatest possible value. Also, how could we make a scenario give us the smallest possible value? So by optimization, we don't just mean largest or maximization. We could mean maximize or minimize. So to do this, what we're going to see is we're just going to go through a handful of examples, and through these examples, we'll see the different things we need to keep in mind when working through these. Okay, so our first example says, what two non-negative real numbers, so that could be 0 and greater, so 0 and then all the positive real numbers, with a sum of 23, so sum of 23, have the greatest possible product. Okay, so let's say that our two non-negative real numbers are x and y, and we want to maximize the product. So we want to say the product of x times y, and we want to maximize p here. We want to get p as big as possible. So in order to do this, we want to see when does this function have a local max. In other words, when does the function, we're going to find this point right here. Now, the problem here with this function that we've written is it's in terms of two variables. So we need to rewrite this in terms of a single variable, either x or y. So we need to use some of the information, some of the other information that's given in the problem, and it says the sum of these values is equal to 23. So if we solve this equation for y, we could just as easily have solved this for x. But what we're going to do is we're going to substitute that in for y over here in our p function, and then we'll end up with a function just in terms of x. So p, we can call this p of x now, 23x minus x squared. And in order to maximize this, assuming that it does have a local max, we don't actually know that yet. But in order to find that out, we need to find the critical points, and we do that by taking the first derivative. So this is going to be 23 minus, whoops, need to use the product rule, minus 2x here. 2x. All right, so to find the critical points, we set that first derivative equation equal to 0 and solve for x. So we get x is equal to 23 over 2. All right, so let's see. That is a non-negative real number. And then to find the second value, we can just substitute that into maybe this equation over here. So y equals 23 minus 23 over 2. So we're going to get a y value that's also 23 over 2. So what we've done is we found two non-negative real numbers. Their sum is 23. And when we multiply these together, p is equal to 23 over 2 times 23 over 2. That's going to be 132.25. Okay, so that's the largest possible product we could get by multiplying two real numbers together whose sum is 23. If we think about this graphically, what that's saying is if we were to graph this p function, or p of x, it's a parabola, it's facing downward. It's going to look something like this. The x coordinate is going to be 23 over 2. So this vertex right here is those coordinates, 23 over 2, comma 23 over 2. Now, let's just kind of talk about this question more generally. So you might be thinking, well, if I was to just kind of guess and check my way through this, I probably could have gotten 23 over 2. That may be true. You may have come to these two values, 23 over 2. However, you might not, guessing your way through this doesn't guarantee that you have the correct values. You might be able to make a really good educated guess, but coming up with 23 over 2 it doesn't give us, as much certainty as we do by going through this maximization process. All right, in our next example it says you are constructing a box from a piece of cardboard that is 2 meters by 4 meters. You cut equal sized squares from each corner of the cardboard, so you may fold the edges to construct an open box. So by open box, that just means a box without closure or a lid. What are the dimensions of the box with the largest volume? Okay, so here we want to maximize the volume of this box. So to find the volume of any three-dimensional rectangular object, we're going to say the volume is going to be the length times the width times the height. And let's draw what we're looking at here. So we have a piece of cardboard that's 4 meters by 2 meters. Now what we're doing is we're cutting out corners here. And it doesn't say what size squares, but depending on what size, or we cut out those squares so that we can fold the flaps up to make this box. So what we want to do is we want to find whatever value x will make this box as large as possible. Now we are trying to maximize the volume, so we want to maximize the v value here. And again, the problem is we have a function v in terms of 3 different variables, L, W, and H. But if the length is 4 for this piece of cardboard, we know that each of these corners, the length of each of these square corners is going to be x. So the length of this piece of cardboard we could say is 4 minus 2x. That's going to be this entire length here. And then similarly, the value here is going to be 2 minus 2x. Okay, and then once we fold up the corners, the height of the box is going to be x. So let's make some substitutions into the volume over here. So the length we're going to say is 4 minus 2x. The width we could say is 2 minus 2x. And the height is just going to be x. Okay, so now we have a function v in terms of x. So I'm going to multiply all of this out. And again, I'm going to rewrite this as v of x. So multiplying this out, we end up with 8x minus 12x squared plus 4x cubed. Okay, so this is a cubic function, and we want to find out where's the relative maximum value for this function. So in order to do that, we need to find the critical points. We're going to do that by taking the first derivative. We end up with 8 minus 24x plus 12x squared. And we want to set this equal to 0 to find the critical point. So 0 is equal to, I'm going to reorder this. Okay, and then to solve this, factor out a 4. Okay, and then this actually doesn't factor, so I need to use the quadratic formula here to solve for x. So x is going to be the opposite of b, plus or minus square root b squared minus 4 times a times c all over 2 times a. Okay, so solving this down and simplifying. Simplifying this now, we're going to end up at 6 plus or minus 2 root 3 divided by 6. If I divide each term by 2, I'm going to get 3 plus or minus square root of 3 divided by 3. Okay, so I'm going to type these. So I have one where it's 3 plus root 3, and then one where it's 3 minus root 3. I'm going to type both of these into the calculator to get some decimal approximations. The two values I get are about 1.577 and about 0.4, let's say 23. All right, so I have two values, so which one could it be? Well, let's just look up here to the piece of cardboard. Well, x, because if we look at this short side, the x value cannot be bigger than half of whatever that value is. X cannot be bigger than 1, because if I have cutting out pieces that are bigger than 1, I'm going to cut more than that length when I cut both of those out. So 1.577 cannot be the value for x. So the value for x here is going to be 0.423. Okay, so what we're trying to find are the actual dimensions. So 0.4 of the box, I should say. So the actual dimensions of the box. So we have the two dimensions in terms of x here. So I'm just going to substitute those values in to calculate. So I don't remember what I was calling the length and what I was calling the width. I guess let's call this the width, and that's the length. That's what I did over here in this equation. So for the width, kind of running out of room, but I'll put the answer just right here. So for the width, we're going to get 2 minus 2 times 4.23. So 2 minus 2 times 0.423, and that gives us about 1.15, let's call it 5, I guess. And then for the length, we're going to say 4 minus 2 times 0.423. And that gives us about 3.155. So those are the two values for the length and the width that'll maximize this box. So what did we find? We find the length and the width, and then the height of the box is just this x value down here that we calculated. One thing I'll say before moving on, since we were maximizing this volume equation, and what we did was we found out what the critical value was of that, and the critical value is just telling us where the value of the derivative is equal to 0. In other words, when is the tangent line horizontal? In other words, when does the function change from increasing to decreasing or decreasing to increasing? This function is going to change from increasing to decreasing at this value. So it was going to do something like this. And this point right here was 0.423. So that tells us where we have that maximum value. And 1.577 that we found is going to be the minimum value. So you can look at the graph of this and see that these values show up in these locations on the graph. We could have also created the interval chart, the horizontal interval chart with these critical values, and then tested points to see where we go from positive to negative, and that also gives us the maximum value. But we didn't need to test both points here because looking at what the image or what the piece of cardboard looks like, we were able to toss out that 1.577. We knew that was not a possible value. All right, in this next example, it says you have 160 feet of fencing to construct a rectangular pig pen against a barn. What are the dimensions of the pen that will maximize the area? So what do we have? We have let's say we have a barn here. It's kind of long and skinny. And then we want to build a pen here. We want to get the area of that pen to be as big as possible based on the 160 feet of fencing that I have. So what are we trying to do? We're trying to maximize the area of this. So the area of this is going to be, let's call this length and width. So we want to maximize the length times width. So again, it's always useful to remember what we're doing. So we want to maximize A. All right, again, this equation is in terms of L and W. We need to get this in terms of a single variable. So the other piece of information we have is that we have 160 feet of fencing. That fencing is going to go along 3 sides here. Okay, so we have L plus W, and then we have another L. So we have 160 feet of fencing is going to equal 2L plus W. So we want to solve for one of these variables and then substitute it back over into the equation for A that we have. So I think I'll just say 160 minus 2L is equal to W, and that's what I'll substitute in. So A is equal to L times 160 minus 2L. So we have a function in terms of L. A of L is equal to 160L minus 2L squared. Since we want to maximize this, we want to find the local maximum value. To do that, we find the critical point, and to find the critical point, we're going to take the first derivative. So this is 160 minus 4L. I want to set that equal to 0. And solve for L. So doing this, L is going to be 40 here. Okay. Now I kind of touched on this in the last example, but we were to test this using kind of the first derivative test. Well, the smallest value possible for L is going to be 0. And the greatest possible value for L, I mean, it certainly can't be greater than 160. I guess it could, and I don't know what's possible. Maybe something slightly less than 80 makes sense, because we need to have a little bit left over for the width. So it makes sense that our domain is something between 0 and 80. So let's pick values in each of these intervals just to verify that 40 is actually the local maximum value. And again, we're going to plug that into the first derivative. So if I substitute in, I don't know, maybe 1 here, 1 into that first derivative, I'm going to get 160 minus 4, so that's a positive value. And then let's pick a number between 40 and 80. How about, I don't know, 60? When I substitute 60 in, here I get negative 240. 160 minus 240 is a negative value. So what we see is we're going from an increasing function to a decreasing function. So the graph going something like this. So it makes sense that we have our maximum value right here. Okay, so the maximum value for L is going to be 40. If L is 40, let's substitute it into this equation. I'm going to have 160 minus 2 times 40 is 80. So W is going to be equal to 80 here. So the dimensions, we're going to have a length equal to 40, feet, and then the width here is 80 feet. And those will be the dimensions that maximize the area. Okay, in this last example, it says, find where the line y is equal to 8 minus x is closest to the point 0, 0. So when is this line closest to the origin? When we're talking about distance, in this case, we're going to use the distance formula. So the distance is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared squared. And we want to get, so just to recap or refresh what this distance formula is telling us is if we have 2 points, let's say x1 comma y1 and x2 comma y2. If we want to find the distance in between them, we just plug in the coordinates in here. So we already have the coordinates for one of these points. It's 0 comma 0. So I'll substitute that in here. So d is going to be the square root of x2 minus 0. So I'm just going to say x here. So x squared plus y squared. So again, we want to see where is the distance. So we want to minimize, in this case, we want to minimize this distance d. Now, in order to minimize this, we need to take the derivative, but we want the derivative, or sorry, we want the function to be just in terms of a single variable. So if I can rewrite x or y in terms of the other variable, we can do it. And this other information we have the fact that y is equal to 8 minus x. So we'll just go ahead and substitute that in for y. So we have d is equal to square root of x squared plus 8 minus x getting squared. So now we have a function in terms of x. That's just d of x. We can write it. And what I'm going to do is I'm going to rewrite the square root with an exponent of 1/2, because when we take the derivative, we'll use the power rule. So in order to minimize this, we're still going to take the first derivative, and then we'll verify that the critical points we have are in fact a local minimum value. Okay, so the derivative here, we're going to say d prime of x is equal to 1/2 x squared. Actually, before I get to this, I want to expand the 8 minus x squared. So I'm going to expand this. So we get 64 minus 16x plus x squared. When I add that to this x squared, I'm going to end up with 2x squared minus 16x plus 64. So I use the power rule, 1/2 times everything inside of here. And then we need to lower the exponent by 1. And then I need to use the chain rule. So I need to find the derivative of the inside part. So that's going to be 4x minus 16 here. So that's the derivative. To find the critical point, I need to set this equal to 0. But before doing so, I'm just going to rewrite this in a little bit of a cleaner way. So in the numerator, I'm going to have 4x minus 16. In the denominator, I'll have, well, this 1/2. I can have a 1 in the numerator and a 2 in the denominator. And then I'm left with 2x squared minus 16x plus 64 raised to the 1/2. And I want to set that equal to 0 to find the critical point. Okay, so when is a fraction equal to 0? A fraction is equal to 0 when the numerator is equal to 0. So this looks pretty complicated, but all we need to do is set the numerator equal to 0 to find the critical point. So x is going to be 4 here. So let's test that. We're going to test values for x into the first derivative to verify that 4 is actually a minimum. And this will be a minimum if the function is going from decreasing to increasing. So what's the easiest value to test here? Probably 0. So plugging 0 into this first derivative, it looks like I get negative 16 in the numerator. And then plugging in 0 into the denominator, well, these two terms are going to go to 0, so I just have a positive value in the denominator. 64 square root of 64 is 8. 8 times 2 is 16. So I have negative 16 over positive 16. That's going to be a negative value. And then similarly, probably the easiest thing to do here is pick a really big number, so maybe 100. In the numerator, I'm going to get a positive value. When I plug in 100 into the denominator, I also get a positive value. Positive divided by positive gives me a positive. So because we're going from an interval with negative values to an interval with positive values, that means that 4 is in fact the value for x that minimizes this. Okay, so plugging 4 up into here for x, we can get our y value, and we're going to get a y value of 4. So the coordinates that are going to minimize the distance, or I should say the coordinates of the point that's on the line that is closest to 0, 0 is 4, 4.